Estimator.
Okay, well, thank you very much for the invitation, and thanks for organizing this, both the seminar and of course the workshop next week. So I'd like to tell you about a recent paper with Eliana Duarte and Orlando Marigliano that we completed at Max Planck, and this will be published in Berkeley. And this picture is an example that will run throughout the talk. So today we're going to talk about discrete statistical models. So it's going to be a statistical model on a finite state space. And our state space is the first n+1 non-negative integers. So 0, 1, 2, up to n. Those are the states. So we have n+1 states. And a probability distribution on that state space is a point in the standard n simplex. So it's a vector P0, P1 up to Pn of positive real numbers that sum to 1. So today I will focus on the interior of the simplex. I'll assume that all probabilities are positive. So then we have data, we make observations, and we summarize these observations in an empirical distribution. So we observe each state a number of times. Then we record that, call that UI, we divide by the grand total, and this gives us an empirical distribution U that's also in the simplex, and let's assume that every state was observed at least once. So UI is a positive rational number. It's the fraction of samples, observed samples, that were in state I. The maximum likelihood estimator of this model is a function from the simplex into the model, and it takes U, the empirical distribution, to P hat, which is the point, or is a point in the model that best explains the data in terms of the likelihood paradigm. So P hat is the maximizer of the log likelihood function. And the log likelihood function up to an additive constant is the following function. It takes a point P in the simplex, it maps it to the sum over all I, Ui times log Pi. So this is well defined, right? Because Pi is a positive number between 0 and 1. And so this is a negative value. And then among all those negative values, we're looking for the largest one. Typically, this will be attained at a unique point P hat, and that's called the maximum likelihood estimate. And the function that takes our data vector U to the estimate is called the MLE, the maximum likelihood estimate. Now, for convention, sometimes we take U to be a non-negative vector without the summing to 1 constraint. So this might in fact be the vector of counts. Then I simply define the MLE to be the MLE value that I would get from this retraction. So this map is a retraction. So it turns out that it's the identity on M, and it's this function we're going to be interested in. And please interrupt me at any time. So if there's questions, you can put it in the QA, and then Elizabeth, I guess, will interrupt. So the way to think about this is the following picture. This comes from a book called Algebraic Statistics and for Computational Biology with Leo Pachter. And here's a cartoon. So this triangle is our n-dimensional simplex. The model is this red curve. Typically, in the statistical scenarios, these models are the image of some parameter space. So there's some other parameter space that maps to the model. Then the data, we have this data vector here, this point U in the simplex, and the goal is to find a nearby point in the model. So there's some metric here, in this case, the Kullback-Leibler divergence, not quite a metric, but almost, according to which we're finding the closest point P hat. And if the model comes in its parametric form and we have some kind of identifiability, then there will be a corresponding unique theta hat, and then those are the maximum likelihood parameters, and this is the maximum likelihood distribution. So that's the goal. The goal is we have a map, that takes every interior point of this triangle and maps it into the red model. And this map is a contraction. It's the identity. It's continuous. It's the identity on the model. So independence models are sort of the paradigm, the simplest one. So let's talk a little bit about the simplest independence model, namely for two binary random variables. So our notation n would be 3. So there are 4 states. So we have two binary random variables, and there are 4 possible outcomes. Let's say heads, 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 tails, tails, heads, and tails, tails. So the model of independence is a surface inside the interior of the 3-dimensional simplex, the tetrahedron. Algebraically, the points in this model are 2 by 2 matrices of rank 1. So rank 1 codes the independence, and they're supposed to be positive numbers that sum to 1. The data table is a non-negative integer matrix U, typically also positive, and throughout, I'm going to use this notation, U bar for the sample size, and then U scaled by that will be the empirical distribution. So in this case, we can write down the maximum likelihood estimator quite explicitly. So we're taking our data U, our empirical counts, and we're calculating p hat as follows. So these are the 4 coordinates. So the way we do this is we calculate the row sums and the column sums of our empirical table. Then we multiply the entries in the row sum vector with the column sum vector entries. So these are these parenthesized products. And then we need to scale by this, divide by the square of the sample size. And then these are the formulas. Okay? So if you look at these formulas, you observe, first of all, that these are rational functions. Right? So the MLE is a rational function of the data. So this is a rational function of the unknowns U0, U1, U2, and U3. It's a homogeneous function of degree 0. It's the ratio of 2 homogeneous quadratic forms. Each coordinate is the ratio of 2 homogeneous quadratic forms. And then finally, there's an algebraic identity. If you add up these 4 rational functions, then amazingly, a miracle happens, everything cancels out, and you get 1. If you don't get 1, that means you made an error. Right? If you work with these kind of models, and then in Mathematica, Sage, Oscar, or Macaulay, you don't get 1, then you have to go back, you have a typo somewhere. Now, some people that you might have met among your applied math, statistics, or engineering friends, they might call this kind of thing an analytic solution. Okay? Now, I don't like this term analytic solution because it suggests that analysis is a very useful subject for statistical inference, which it is, but so is algebra, right? To me, this is certainly not an analytic solution. This is an algebraic solution. So if anybody ever speaks to you about analytic solutions and there's a pinch of algebra in it, please call them out on it. These things are algebraic solutions. This is an algebraic solution for the MLE problem for this model. Now this picture, due to near eye, it says more than 1,000 words, right? So n is 3, we have our surface in the triangle. The empirical distribution is somewhere here or here typically. So the surface divides the tetrahedron into 2 regions. One side we have positive correlation. On the other side, we have negative correlation. And then on the surface, we have perfect independence. And this picture is sort of iconic, both for our field, algebraic statistics, and for a nearby field called information geometry, which is more concerned with the differential geometric aspects of these models. Now, the independence model belongs to a larger class of models, so-called graphical models. Now, graphical models come from graphs, and they come in 2 flavors, undirected and directed, but let me go here over the undirected case. So I'm going to fix an undirected graph G, whose nodes are random variables. Each of them is a random variable in this talk with finitely many states. then the graphical model, MG, the undirected graphical model or Markov random field, lives in the n-dimensional simplex, where n+1 is the total number of states in the joint distribution. So n+1 is a product of numbers, each of which is the number of states at a given vertex. So if I have a binary model, if every state is binary, and I have 10 nodes in my graph, then little n would be 1023, because there are 2 to the 10 joint states, and then -1 because I'm in the simplex. Now, the nicest graphs, G, are those that are chordal or decomposable. So if the graph has the property that whenever there's a cycle of length 4 or more, and you can shorten it by the chord, then we're going to say the graphical model is decomposable. Now, it's known that in this decomposable case, again, we have an algebraic solution. Namely, each coordinate, pi hat, of the MLE is an alternating product of linear forms. The combinatorics of this product is given by the maximal cliques and minimal separators in this graph. So if you go back to our formula, you can see not only are these rational functions, but you can see that both in the numerator and in the denominator I have a product of linear forms. In fact, linear forms that are sums of the observed UI. And this is going to be true for graphical models. Now, a similar formula exists and is well known for directed graphical models. So you have directed graph, or DAG, directed acyclic graph, or Bayesian networks. Again, then you can write down the MLE algebraically. That will be an algebraic solution, namely as an alternating product of linear forms in the observed counts. Now, a common generalization of both flavors of graphical models are so-called staged tree models. And I'll show some examples. So that's a generalization of these graphical models. And again, the MLE is rational in the same sense. So there's a book from 2 years ago by Collazo, Gergen, and Jim Smith, where they talk about these stage tree models. So these are some examples of models that have a rational MLE of a particular kind that are quite commonly used in statistics and its applications. So here is a tiny example of a staged tree model, and it describes the following experiment summarized in red. So you have a single biased coin, and so S0 is the probability of seeing heads, S1 is the probability of seeing tails, they add up to 1. So the experiment is you flip a biased coin. If it shows heads, you flip it one more time. Okay? So this experiment has 3 possible outcomes, right? So n is 2. There are 3 possible outcomes. So the possible outcomes are tails, heads, heads, or heads, tails. So if you have tails the first time around, you stop. If you have heads, you do it one more time, and then this becomes either heads, heads, or heads, tails. So as a parametric model, so in the parametric form, the model is the image of a polynomial map from delta 1, the one-dimensional simplex that governs our parameters, and we're mapping it into the probability triangle. And the formula is very simple, right? So the probability of observing heads, heads is S0 squared, heads, tails is S0, S1, and then tails is S1, and subject to these constraints. And again, these 3 quantities add up to 1. Now, in algebraic statistics, the first thing we often attempt to do is to find an implicit representation of our variety. So this model can also describe by this quadratic equation. P0 times P2 is equal to P0 plus P1 times P1. And that's a homogeneous quadratic equation inside our triangle. And that carves out the image of this parameterization. This is our model. Okay? Now here is the formula. Again, the MLE is rational. So let's write U0, U1, U2 to be the counts from repeated experiments. Then the maximum likelihood parameters are given by these formulas, S0 hat and S1 hat. And in this case, it's quite easy to understand. So what these represent is in the denominator, you have the total number of coin tosses, right? So if you have U0 outcomes heads, heads, U1 outcomes heads, tails, and U2 outcomes just tails, then the total number of times you tossed your coin in the sequence of experiments is this expression, 2U0 plus 2U1 plus U2. And then we're just recording the fraction of times the coin came out heads. That's 2U plus 2U1. And then tails, which is U1 plus U2, right? And so these two things sum to 1. Then you take these expressions for the S0 and S1, you plug into the parameterization, and you get the formula that's our MLE. So our MLE is a self-map from the triangle to itself, and this is the formula. So the formula is given by these three rational expressions. They add up to 1. And again, you can see the special feature that we've observed before, that both the numerator expressions and the denominator expressions are products of linear forms, when in fact each linear form is a positive linear combination of the counts. So the topic of this talk and this paper is how to be rational. How can this actually happen? So let's make this precise. But before we make that precise, let's ask the same question for the Euclidean metric. So suppose you have M were a model in a Euclidean space, and the notion of proximity comes from the usual Euclidean metrics. Let's say phi is the map that maps Rn to the model by the usual, high school Euclidean nearest point map. Then I claim that phi is a rational function if and only if M is a linear space, right? So if you have a linear space, then we know from high school analytic geometry that there's a rational formula that computes the closest point on a line or plane. But I also claim that that's the only scenario. So any other scenario, when you calculate the closest points, you have to take square roots or do some other thing, and you no longer have a rational function. So we'd like to ask the same question in the maximum likelihood setting, where the Euclidean distance is replaced by the Kullback-Leibler divergence. So the question is, in the maximum likelihood framework, which models play the role that was played by linear spaces in the Euclidean setting? So our problem is to characterize all models inside the open probability simplex such that the maximum likelihood estimator, our retraction from delta M to M, is a rational function. We observed, as I said, lots of examples of statistical relevance that fall under this category, such as decomposable graphical models, Bayesian networks, and more generally, stage tree models. So this is the problem. Maybe I should pause for a second. Is there any question about the problem? Well, this is the problem we're going to answer. Okay, I'm not hearing anything. Everybody is dark. You guys following?
Okay. Yes, we are.
Yeah.
Okay. If there's no question, then let's jump into the theorem. So this is the solution. Okay. So M here is quite general as any subset of the open simplex. And if you think this through, it turns out that the fact that this is actually a variety, a semi-algebraic, will follow as a consequence, right? So if you have a model that has a rational MLE, then it follows that the model has the MLE as its parameterization and is therefore an algebraic variety, a semi-algebraic set. So the following are equivalent. 1, the model has a rational MLE. That is to say, the function phi, the MLE function, is a rational function of the data of the U vector. 2, there's a so-called horn pair. It's a pair H comma lambda, such that the model is the image of the associated horn map. So I need to define, to tell you what is a horn pair, and then that model will be the image of the associated horn map. Condition 3, again, something I need to define. There exists a discriminantal triple, so that's a triple A delta M, such that the model is the image under the monomial map given by delta and M of precisely one orthant in the projective dual of the toric variety given by the matrix A. Okay, that's a mouthful. So I will need to explain all of these things, but the theorem isn't done yet. So if one, and hence all of these conditions, are satisfied, then the MLE has a particular form. It's either the horn map itself, or it's the composition of the linear map, H. H is actually a matrix, followed by the monomial map. So this is linear followed by monomial. This will explain the product of linear form. And then this holds in the orthant, right? So we're using positive orthant. Now I will explain this theorem. It's, my opinion, a very nice theorem. But what makes it nice is that it rests on the work of others, right? So we're really standing here on the shoulder of giants. So there was earlier work in complex algebraic geometry, in particular by Kapranov. So Kapranov has a paper from 1991 where it characterizes a discriminantal hypersurfaces in terms of the logarithmic Gauss map. So the logarithmic Gauss map is a very important player. This thread was picked up by Huh, who published a paper in the Algebraic Statistics journal called Varieties with Maximum Likelihood Degree 1. So June observed that Kapranov's solution really applies here. Now the results thus far were really statements in complex algebraic geometry, in fact, over any field pretty much. And our contribution is to take that work and turn it into a real algebraic geometry setting that's relevant in statistics. So there was a number of things that still needed to be done from the work of Kapranov and Huh to get it into the actual setting that we care about in statistics, the real positive setting, and that's what we did in our paper. Okay, so I need to explain to you now what these things are. What's a horn pair and what's a discriminantal triple? Let's start with horn pairs. So I'm going to look at a matrix, an M by N plus 1 matrix, and this has integer entries and 0 column sums. Okay, so the number of the columns correspond to the states in the model. So there's one column for each state, and there's a number of rows, M. We don't know yet what that is. And then we're going to look at the alternating products of linear forms that are specified by this matrix. So here's what we do. And this is HU to the power HJ. So this is Huh. Think about June Huh. Right? So HU to the power of HJ. So by definition, this means a vector is raised to another vector. So HJ is the column vector for the jth state. So I'm raising a vector of length M to another vector of length M. And I do that by multiplying the entry-wise power. So I from 1 up to M. Then HU is the matrix vector multiply. So I take the matrix U, H, I multiply with the column vector U. And then in the ith coordinate of this product, I see the usual expression. So that's the ith entry in the column vector HU. That is a positive number typically here. Well, I know this yet, it's just some number. I raise it to the ij entry of our matrix, and that product is this quantity. And these alternating products of linear forms have degree 0. This is just a translation of the 0 column condition. I'm going to say the horn matrix H is a friendly matrix if there exist real numbers, lambda 0, lambda 1 up to lambda 0, lambda 1 up to lambda n, such that this identity holds, this is equal to 1, as an identity in the field of rational functions in U0, U1 up to UN. Okay, this is a identity. So if there exist multipliers, lambda 1, lambda 0, lambda 1, and so on, so that this rational function identity holds, then I'm going to call the matrix friendly. Now, if this holds, let's look at the rational map that simply takes our vector u to the vector of sum ends in this identity. Right? So I'm taking u and I map it to this vector of sum ends. This is a self map of real n+1 space. And you can see what this happens. This image lies, the image lands in the hyperplane where the coordinates sum to 1, if things are friendly. I'm going to say the pair H lambda is a Horn pair if the following things hold. If the H matrix is irredundant in the sense that no row of H is a multiple of another row, otherwise you can aggregate them. If this map is defined for all positive vectors, well, it could happen that these Hij's are negative entries, so what we want to avoid is dividing by 0, right? So if you plug in positive values for the U, you're not supposed to get 0. That's a requirement, so this map is defined for a positive vector. And finally, it should map positive vectors to positive vectors. Okay? So these are a lot of hypotheses. And then under these hypotheses, the Horn map is simply that very map, but restricted to the simplex. So then it becomes actually a self-map of the simplex.
So Bernd, we have a question. So Alex asks, what are the lambdas? Are they positive between 0, 1, or any real number?
Yeah, just some, all I'm saying is they're real numbers. So they, a posteriori, they will be rational numbers, but they could be positive or negative. A priori, they could be positive or negative. I will then, this can be then, so then it turns out that the signs inside H can compensate for possibly negative lambdas. But a priori, they can be, they're just a bunch of numbers, and but when can, a posteriori, they will be rational. Let's look at this in our running example. Okay, so remember the running example was this model, so this quadratic curve inside the triangle. In red, the story, right? You flip a biased coin. If it comes up heads, you flip it again. This is the stage tree representation of this red model. In this case, the Horn matrix is a 3 by 3 matrix. So there are 3 columns because there's 3 outcomes. M is also 3. So here M is 3 and N is 2. In this example, the lambda that works is the vector 1, 1, minus 1. So in this case, they're integers, but you see that minus 1 can occur. The maximum likelihood estimator is exactly the function we saw earlier. So it's the self-map from the triangle to itself, given by the aforementioned algebraic solution, not analytic, algebraic solution. And this is exactly this formula. So lambda 0 to the HU to the H0. So you have to unravel this, right? So this takes a little practice to unravel these things, but then this is what you get, right? So what makes this unraveling slightly tricky is that the entries of the Horn matrix H, they play 2 roles. They occur twice, right? They occur as coefficients inside linear forms. So they occur as coefficients inside the linear forms, but they also occur in the exponents. Right? So we're going to recycle the Horn matrix entries and use them twice as coefficients inside the linear forms and as exponents in these numerator and denominator rational functions. Okay, so it's clear. So this example and these definitions, if you were able to follow all that, should tell you what this is, okay? So at this point, I've explained the statement of the equivalence of 1 and 2, but I have not yet said anything about 3, right? So if this holds, so this says that if we have a model that has ML degree 1, then it has precisely this very special form, in particular, the numerators and denominators of each coordinate in this rational function is a product of limits. Now, who is Horn? Let me talk about this a little bit, and along the way, I'll inflict some German language text on you. So there are a number of mathematicians with that last name, both dead and alive. And this one was Jakob Horn. So Jakob Horn was a German mathematician who studied differential equations. So he studied differential equations. He was the son of a carpenter and a farmer, right? So the son of a farmer. And only under very serious financial sacrifices of his parents, he could attend the higher school in Michelstadt and Gießen. These are place names. And what I like about this, these are place names were very close to where I grew up, in the neighborhood of Frankfurt in the state of Hessen. So Jakob Horn was born in February 1867 in a tiny village called Rehbach near Michelstadt. And he died in February 1946 in the same tiny village near Michelstadt. His dissertation led to the publication of this paper in Mathematische Annalen on the convergence of hypergeometric series in 2 and 3 unknowns. So he was an analyst who studied differential equations, in particular hypergeometric differential equations. Hypergeometric differential equations are absolutely beautiful, very combinatorial, very algebraic, in my view, very important for applied algebraic geometry in general, and potentially algebraic statistics in particular. Here, this was another entry I found online. So he came from very, very simple circumstances. Here it says only under great financial sacrifices of his father, right? So one source talks about sacrifices by both parents. The other source only speaks about sacrifices of his father. Then he went to the school, and the director of the school supported him. He was a big supporter. He married the daughter, right? So he was later the Schwiegervater. And then he studied with Weierstrass. He met people that are prominent mathematicians, Weierstrass, Kronecker, Fuchs. He went to Heidelberg, Freiburg, and then for many, many, many years in 1907, he became a professor at Darmstadt, and he taught there until 1934, until he was retired. So not only did he grow up very close, died very close to where I grew up, he also was a professor at the university that I studied. So this is Jakob Horn, and this is the Horn pair. So this was found and developed by Kapranov. Discriminantal triples. So let me give you now the even more complicated definition of the third equivalent condition, but this is the one I like best because it ties in to toric geometry, and as we all know, the world is toric. Section 8.3 in the new book with Mateusz is called The World is Toric, so this connects us to toric geometry. So a discriminantal triple is a triple A delta M, and A is an integer matrix. Delta is something called the discriminant or a discriminant associated with this matrix, and M is one of the monomials in this discriminant. Now, there are many sources on these things. There's an overwhelming source, the green book by Gelfand, Kapranov, and Zelevinsky, which I strongly recommend to those who like to be overwhelmed, but of course there are other sources too. So rather than giving you the full definitions, I'll just give you one example. Okay? Very, very simple example, and that's the example for this model. Flip a coin, flip it again if it comes up heads. So in this case, the integer matrix is this 1/3 matrix. So A is an integer matrix where the all one vector is in the row span. Well, this obviously has the all row one vector in the row span. So this is our matrix in this example. Now, this is connected to the Horn matrix because this matrix is a basis. The rows of this matrix are a basis for the left kernel of H. Well, because the columns sum to 0. Now, the toric variety given by this matrix A is very simple. It's just a point, right? So in general, an integer matrix always defines a toric variety. Typically, we're assuming that the all one vector is in the row span, so it defines a projective toric variety. And again, this is not an outlandish concept because after all, the world is toric. So here the toric variety is a point in the projective plane. It's the point with homogeneous coordinates 1, 1, 1. Now, whenever you have a toric variety, projective toric variety, or in fact any projective variety, there is a dual variety, right? So under the usual duality between points and hyperplanes, the dual variety is the set of all hyperplanes tangent to the primal variety somewhere. And in this case, the dual toric variety is simply the hyperplane, the line that recycles these coordinates as coefficients for the linear form. Right? So the toric variety is the point, and the dual toric variety is the line. And this you can do more or less for any integer matrix. Now I'm going to look at any polynomial. I'm going to call discriminant any homogeneous polynomial that vanishes on this dual variety. Right? Now, of course, there is a unique up to scaling irreducible polynomial that enjoys this property, right? So this would be officially the discriminant. It's the irreducible polynomial that vanishes. But maybe I don't like this polynomial. I will take some other bigger polynomial that also vanishes, right? Nobody prevents me from doing this. So I simply multiply this polynomial by x3 minus 1, my choice, right? I get this polynomial, and I call that a discriminant. So it's a indefinite article discriminant associated with A. Again, A is an integer matrix. Delta is any homogeneous polynomial that vanishes on the dual toric variety YA star. Finally, M is any monomial that you see. Now, you take one of these monomials and mark it in blue and call it the leading monomial. So in this case, I simply make the choice. I say I like this term, and that's my boldface M. Now, to move us a bit closer to probability, we're going to divide by M. And the equation delta 0 becomes an equation like this. Something plus something plus something is equal to 1, right? Because the blue term becomes 1. And so this is equivalent to our discriminant equation delta equals 0. Now, this data defines a monomial map, right? You simply take the monomials, the Laurent monomials you see on the left side with sign, Alex, with sign. And this defines a monomial map, right? So it defines a monomial map that takes x1, x2, x3 in this case, the vector of Laurent monomials you see in this partition of unity. Okay? So every discriminantal triple in this form gives us a map phi delta M. And that now explains the theorem. So the following are equivalent. We have rational MLE, there exists a Horn pair, and there exists a discriminant. Now these two conditions, 2 and 3, they're quite different in their philosophy. So 2 is a very good concept for the analysis. So if you give me a model, this is a very, very good way to sort of analyze and structure the model, is to identify the Horn matrix. 3 is much, much better for the synthesis, for the generation. So if you want to generate a wealth of models with this property, then 3 is the way to go. So 3 gives you a way to build these models. So it's very good for the synthesis of these models. 2 is very good for the analysis of these models. That's why we have these two conditions. So let's go back to stage trees. So stage trees are examples of this. And this is worked out in the paper, for example. So if you take the 4-chain model, so the graph, that's the 4-chain, then that's n equals 15 with binary states. This picture shows this as a stage tree. Here, it's hard to see. This is the Horn matrix. So the ones are ones, the dots are zeros, and the dashes are minus ones. So this is the Horn matrix, a big matrix with 16 columns and I forget however many rows. F and S stands for florets and separators. And then for any stage tree model, you can write down the maximum likelihood estimator in the automatic way given by the theorem. So we can analyze the situation and really explain the formula in the Gergen-Smith book. But we can also turn this around and think about this as the outcome of a synthetic process that makes models. Let's be very specific, right? So in this case, for this model, for this undirected decomposable graphical model, there is a matrix A, and this matrix is not the model matrix that you're familiar with from the standard literature in algebraic statistics. So in the standard literature in algebraic statistics, there would be something called the model matrix with 16 columns. This is not the matrix A we're using here. The matrix A here is a different matrix. It has 21 columns and 13 rows. The toric ideal for this different matrix is written like this. So the unknowns here are the S's and the F's that describe the combinatorics of this tree. Now this is a toric variety. Well, the world is toric, right? So this is a toric variety of dimension 12 and degree 141. It lies in a linear subspace of codimension 2 in P20. What we really care about is the dual hypersurface, right? So we take this toric variety, we calculate the dual, and the dual is a hypersurface given by this beautiful equation. We choose one of the terms of this degree 7 hypersurface, namely the blue term, and then we divide through this, and then this gives us exactly the formula. So this is an interesting topic that I think deserves further study. Are there any questions? Maybe I'll pause for a question. Okay. If not, we're going to wrap up. So I'm going to come to the conclusion, and we're going to end a couple minutes early. So I'm going to end by simply going over the abstract of the talk. So the abstract of the talk and of the paper reads like this. A discrete statistical model is a subset of a probability simplex. Its maximum likelihood estimator is a retraction from that simplex onto the model. It's a continuous self-map from the interior of the simplex to itself, whose image is the model and which is the identity on the model. We characterize in this work all models for which this retraction is a rational function. What's new is that this is a contribution via real algebraic geometry, which rests on complex abstract algebraic geometry results by Huh and Kapranov. And the context of this is Horn uniformization. So Kapranov in 1991 had this brilliant insight that 100 years earlier, the work of hypergeometric functions by the analyst and farmer's son, Jakob Horn, was highly relevant. We present an algorithm, that's the synthesis. So part 3, the dual toric varieties allow us to give an algorithm for constructing models with rational MLE, and we demonstrate this on a range of instances, such as stage trees and some decomposable graphical models. Our focus, again, as I said, lies on models that are familiar to statisticians, so we don't want to dream up some outlandish things, but familiar models such as Bayesian networks, decomposable graphical models, and stage trees. Now, in my mind, this is not the end of it. In some sense, it's the beginning. This raises many, many questions and open problems, and I'd like to close on 2 open problems. First open problem is to extend our results to the Gaussian case. Right? So this was for discrete models where the ambient space is a simplex and where the information geometry, really the differential geometric structure, comes from the Kullback-Leibler divergence that gives us the structure, the geometric structure on the simplex. Now we're going to replace, in the Gaussian case, the simplex by the cone of positive semi-definite matrices. So the PSD cone now plays the role of the simplex, and it comes with its own metric, with its own maximum likelihood geometry. And we would like to find a similar theorem for the Gaussian case. It turns out that these formulas as alternating products of linear forms, they do hold for graphical models, but they do not hold in general. So in the Gaussian case, there are models that are rational, but where the rational functions do not have the special form, and that we saw in the simplex case, and we do not know yet in general everything that's going on in the Gaussian case. So that's an open problem. Another very tantalizing open problem is the following, back to the discrete case. Let's say we fix n. So we're fixing the number n+1 of states. Then we believe that up to a natural equivalence, there are only finitely many models with rational MLE in the simplex. And then we might as well be bold and ask the same question in the Gaussian case. So we're conjecturing that for fixed n, a model with rational MLE has bounded degree, that the degree and MLD, that the degree will be bounded by some number that depends only on n. Okay, that's it. Thanks for your attention.
Thank you, Bernd.
Maybe I put the theorem up. Yes.
Okay, so there are a couple of questions that sort of came up at the end. So I will, if people are able to ask them themselves, I will do that. So let me see. I'm going to just bear with me real quick while I get to the attendees list. So Rudy, I think that you were, let's see. So Rudy, you're allowed to talk now. So will you ask your question?
So we can see each other.
Just a moment. I cannot make myself, I don't know, video actually. You see my host, but yeah, I don't think it's let me show my video. But so I'm not like, this is my first time I've seen this home matrix. And just like, it's really nice, I like it, but how did you how can you compute the home matrix from the model? And for example, for this simple example you gave us, like after the slide, like one page next to this slide, I think, you show some simple example. How did you compute the home matrix? Yeah, the simple.
Well, I think the easiest way for me is to work my way back. So if you have a model that you know and like,
yeah,
then you have a formula for the MLE, right?
Yeah.
But then you can rewrite this formula in this kind of fashion, right? You can take this formula and organize it into some polynomial that looks like delta, where one distinguished term plays the role of 1.
Right.
Now, the nice thing about projective geometry duality, it works both ways, right? So you can then back dualize and recover the toric ideal. And then once you have the toric ideal, you get the matrix A. And once you have the matrix A, you get the matrix H.
Yeah.
So you can run this process either forward or backward. So, but if you have a model that you know, you can run it backwards, and you can get the H and the A by just interpreting the MLE formula you know.
Right.
But it works both ways.
Yeah. And from there, how can you compute the form matrix? Because it looks like really complicated, and it's not like I can calculate the matrix A for toric ideal. That's kind of really
but the important. So this is the single most important message here for you, Rudy, is that the matrix A here has nothing to do with your matrix. It is not the model matrix. It's a very different model matrix. And it's a little subtle. It's a matrix that governs the structure of the MLE formula, the different matrix.
I see.
We have to, in each case, you have to analyze this. So as I said, we analyzed this in the stage 3 case. I think there's a recent paper by Seth and a student where they came up with another classes of models that have ML degree 1. So I think in any particular case, you can analyze this and maybe recover the Horn matrix. But it's not entirely, it's not obvious.
Okay. Got it. So I'm gonna practice then. I might bug you later, but thank you.
All right. So Seth said Jane Coons is the one who is the co-author on that paper, and she's giving a talk next week. So the next question we'll have Alex Heaton. You were going to ask a question. You're allowed to talk now. You'll have to unmute though.
Okay. My question was about the delta
that defines the dual hypersurface on the last slide. If you multiply it by some other factor, then does the stage tree model change in some predictable way?
It will be a different model. So it changes the model, it changes the number of states. Is it predictable? Not really. It can be quite, as far in our experience, it can be quite unpredictable. So, of course, my co-authors, if either of them is here, can contradict me, but it's a little not entirely obvious to see what happens when you take a different delta if you multiply with something.
Okay, thank you.
All right. And then next, Serkin Hoshton had a question. So you're gonna have to unmute yourself.
I did. Do you hear me?
All right, great. Yeah.
Hi, Bernd.
Hi.
My question was about your first open problem at the end. It's a simple question. So when you said extend this result to Gaussian case, so we need to look for rational functions of what? So is it going to be the empirical
So
covariance
let's
matrix?
say it's a map. So in the Gaussian case, we have the sample covariance matrix.
Okay.
Let me assume it's positive definite, and it maps to the model, right? So I have a model that's a subset of the so I have a self map of the PSD cone that's a contraction onto the model.
Okay.
And under what circumstances is this a rational function?
Thank you.
That's actually, this problem, as far as I know, maybe Seth can comment on this. This is not entirely clear even in the linear case. In the linear case, there are two possibilities. A linear space can either be a covariance matrix or a concentration matrix. In one case, it's an exponential family. In the other case, it's not. So even in those cases of L and L inverse, characterizing this situation, to the best of my knowledge, is open. So many of us these days are very interested in linear spaces of symmetric matrices, LSSM. And even in that case, I believe this problem is open.
Okay, thank you.
Seth, did you want to add anything to that since Bernd had mentioned you? We'll see. No, he doesn't have anything about that. He doesn't, okay.
You didn't solve it, Seth, you didn't solve it yet, no?
Let's see. Not yet, exclamation point.
Okay, okay.
All right. So I did have a question. So you guys figured, so you applied these results to the stage tree case. In your paper, did you do any, work out any other examples in full detail?
In terms of a complete family, we only did the
Yeah.
stage.
Okay.
So this is sort of an example of this proposition, sort of summarized the stage tree case. We focused on that because this is more general than the other cases, but in principle, one could do the same for, the chordal graphical models or.
Yeah. Okay. Are there any other questions? You guys can either raise your hands or add them to the Q&A. I think though that we've sort of, that I don't think that there's any other questions popping up. So I would like to do two things. We're going to thank Bernd again for his wonderful talk. And then afterwards, we're